finish up our discussion of random events, let's look at independence. So two random events are independent if the order in which they occur doesn't matter. So if we could exchange them, events E and F, if event E happens then event F, or event F happens in event E, it doesn't change either event, doesn't affect the other. And so there's plenty of cases when that's not true. So an example would be if you jump out of a plane, if the event, one event is that you survive your parachute jump, and another is that you put the parachute on, the order is going to matter, right? So if you jump out of a plane and land and then put the parachute on, that's different from putting the parachute on and jumping out of the plane and landing. If we our bags and balls ideas, if we have a bag with different coloured balls, as we draw bags out, then we change the contents of the bag, and so what's gone before affects the likelihood of events that come later. So if we pull out a green ball out of a bag with green and orange balls, then the chance of pulling out an orange ball next increases because now there's fewer green balls. So these are examples of events that are dependent, they're not independent. But in games of chance, we often take some care to try and make things independent. So, for example, if we have a fair coin, then if we toss it once and we get heads, then the second toss we don't think depends on the outcome of the first toss. Regardless of the fact that we get heads or tails in the first toss, the second one will give a separate result. And so that's a clear idea of independence. So how do we formalise that? So here's the formal definition. And it's a little bit odd actually in the face of it, so we'll give the definition and then have a think about it and check that it actually gives us the properties that we expect to have from intuitively thinking about independent events. So the definition is that if we have two events E and F, the probability of E intersection F, so it's probability of the two events happening, of E and F both happening, is equal to the product of the two separate events, the probability of E times the probability of F. And that's the definition of independence. And so we can immediately go back to think about conditional probability and apply that here. So if we remember the chain rule, which I'll just show here, which comes directly from the definition of conditional probability. We've got the probability of E intersection F is the probability of E given F times the probability of F. And when we have independence, then we know that that's equal to the probability of E times the probability of F. And so if we divide through by the probability of F, assuming it's not zero, then we get the probability of E given F is equal to the probability of E when E and F are independent, which is what we'd expect, right? That means the probability of event E happening, given that event F has happened beforehand, is just the same as the probability of E happening. It does not change by the fact that event F happened. So immediately we've got our definition of independence has given us like the core property that we expect independence to have, that whether an event's happened beforehand or not doesn't affect the probability of the event of the other event. One thing just to flag though, because I see sometimes people giving it as an answer in exams and so on or whatnot. Maybe they're getting it off the web, I'm not sure. Sometimes they'll quote this as the definition of independence, that the probability of E given F is equal to the probability of E. But that's not the definition, right? It's a consequence. So the definition is this guy here, right? The one we started with. And this conditional probability relation is a consequence of that definition. And of course, if two events don't satisfy that, then they're dependent events, right? They can either be dependent or independent. There's no other option. And when I'm asking you in exams whether two events are independent, of course you can think intuitively, does one depend on the other and so on, and that's fine. But really, when you're formally asked to check for independence, what you need to do is calculate the three probabilities here. The probability of E intersection F, the probability of E and the probability of F and check whether they're equal or not. And if they're equal, then they're independent, and if they're not, then they're not independent. So when I ask you to check for independence in exam questions and so on, or weekly assignments, I'm actually wanting you to evaluate this expression and check whether there's the equals holds or not. Of course, also use your intuition to think about it. So some quick examples. If I pick a random Leaving Cert student in Ireland, do you think the two events applied to Trinity and applied to UCD are independent? Probably not. If you apply to both, you probably live in Dublin, or if you're interested in coming to Dublin, and so you'll apply. If you apply to one, you'll apply to the other. If you pick a random person in Ireland and ask, are they a Trinity student and do they have brown eyes? That's probably independent, right? I don't think that there's any bias amongst Trinity students to having brown eyes or any other sort of eye colour. Another example is the gambler's fallacy. So people were very interested in this in the 1600s, and still are to some extent. So the idea is that if you flip a coin again and again, then if you get a run of heads, suppose you got 10 heads, which is pretty unlikely, then there's a feeling that you're due tails. And so somehow, after seeing a run of heads, a tails is more likely. And that's a fallacy. If it's a fair coin, if you've had 10 heads, whether it comes up heads or tails, isn't affected. It's still the same. It's still probability half getting heads, probability half getting tails. It doesn't change because they're independent. Even though it's very tempting to think that it does change. So let's try and put some numbers on things. So if we roll two six-sided dice, so E is the event that the first dice is 1, and F is the event that the second one is 1. So the probability, so because it's six-sided dice, that means we've got numbers 1 to 6 when we roll each dice. The probability that the first dice is 1 is 1 over 6, so it's just 1 out of the 6 possibilities. Probability that the second dice is 1 is 1 over 6. Now, the probability set of events that can happen when we roll both dice is there's 36 possibilities. That's all the pairs that we can get from the two dice. And the probability that the first dice is 1 and the event that the first dice is 1 and the second dice is 1, that only happens once, right? There's only one way that can happen. So the probability of that event is 1 over 36. And so if we plug it in, is 1 over 36 equal to 1 over 6 times 1 over 6? Yes, it is. And so these two events are independent. That confirms it. Now let's have the same setup and consider an event G that the dice sum to 5. Now somehow the sum depends on the outcomes of both dice, doesn't it? So it's going to act to couple things together. And so we're going to ask the question, are E, the probability the first dice is 1, and G, that they sum to 5, independent? And we don't really expect them to be independent because the sum depends on the outcome of the first dice. But let's check. So if the dice sum to 5, there's 4 different ways that can happen. It could be a 1 and a 4, 2 and a 3, 3 and a 2, or a 4 and a 1. There's 36 possible outcomes, so the probability of G is 4 over 36, which is 1 over 9. We already know the probability that the first dice is 1 is 1 over 6. And the probability that the first dice is 1 and the dice sum to 5 corresponds to this event here. The dice is 1, the second dice is 4. That's the only way that can happen. So there's one way that can happen out of the 36 possible outcomes. So the probability of that is 1 over 36. And we plug that in and check. 1 over 36 is not equal to 1 over 6 times 1 over 9. And so it follows that they're dependent as we expected. But it's the formal check of the dependencies to go calculate the probabilities and see whether they're equal or not. Let me skip over this. It's just a side comment that if you have 3 random variables, not just 2, and you're interested in whether they're independent, it's not enough for them to be pairwise independent. It's not enough that E and F are independent and F and G and E and G. Instead, you need them to be triply independent, which is this third condition here. And it's a rare thing to come across, but it's worth being aware of. And here is an example illustrating that fact, right? So just you can work through that in your own time.